Hello, and welcome to Aggressive Physics. Today is day 87, and what I'd like to do today is a number of sample problems dealing with waves. If you've noticed, this section of the course is mostly conceptual. There's a lot of terminology and not a lot of practice problems or problem solving. For some students, they find this refreshing because we've done problem solving since the beginning of the course. So at this point, we switch gears a little bit and start dealing with concepts, terminology, definitions, and in some cases memorization. But there are different sample problems we can do. And what I'd like to do today is a couple of sample problems dealing with the entire chapter. Maybe we'll find the frequency of a wave, or use v equals f lambda to find the wavelength. Possibly use the Doppler effect formula. Maybe look at some beats or resonance or different things like that. We might even sketch some waves and try to see the difference between amplitude, wavelength, and possibly frequency. So let's take out the whiteboard now and look at a couple of sample problems that we could deal with over the course of the entire waves unit. So this is day 87, mostly a practice day, and let's take out the whiteboard now. Thank you. All right, because the waves section is not a lot of deep problem solving, what I did is I went through some old exams and I found 10 questions that are indicative of the types of questions that we'll deal with in this chapter. And what I'll do is I'll solve 5 at a time on the whiteboard. These are all multiple choice questions. First one is, what is the period of a periodic wave that has a frequency of 60 hertz? Well, in this case, if the frequency is 60, how does that relate to period? Well, time period is the reciprocal of frequency. So if I take 1 over 60, that should give me the value for the time period. And that's 0.0167. And the opposite of hertz is seconds. Now, if we look through the choices, the one that's the closest to that, and they change it to scientific notation, that would be choice 1. For the second one, the speed of a transverse wave is 12 meters per second. If the frequency is 3 hertz, what is the wavelength? Well, we have to remember our equation for waves, which is v equals f lambda. 12 meters per second equals 3 hertz times wavelength. And wavelength, I don't even need a calculator for this, 12 over 3 is 4 meters. So that'll be choice 4. All right, my next one is the wavelength on the periodic wave shown in the diagram is 4 meters. What is the distance from point B to point C? And it has a periodic wave that looks like this. And point B is here, and point C is here. Now what we need to remember is, what is the distance between those 2 points? And this is the origin here. Well, that looks like half a wavelength. So if the wavelength is 4 meters, half of that should be 2. So that would be choice 2. Now the previous one was 4 and the answer was 4. This one's 2 and the answer is 2. I don't think it's always going to work out that way. But let's do number 4. Sound waves with a constant frequency of 250 hertz. Okay, I'm going to write that. Are traveling through air at STP. Now that is an indication that we're going to have to look on our reference table and look for the speed of sound in air. STP is standard temperature and pressure, and it's 331 meters per second. We want to know the wavelength, so v equals f lambda. 331 equals 250 times wavelength. and the wavelength will be 331 divided by 250, and we should get 1.324 meters. And that's going to be choice 2. All right, as we continue our practice problems, we're looking at number 5 now. And number 5 says the diagram shows two waves traveling in the same medium for the same length of time. The two waves have different, and the waves look something like this. We have that, and then we have that. Now, from this diagram, which isn't as good as the one on the actual exam, we're going to see that the wavelengths are the same. We're going to know that if the wavelengths are the same and they're traveling in the same medium, that means the speed is the same, v is the same. That means the frequency is the same. So, the choices are amplitude, frequency, speed, and wavelength. Now, you probably noticed that the heights were different originally, so the one thing that is different is the amplitude. So amplitude is different, and that's choice 1. You might have skipped all these parts and just known directly that it was amplitude. All right, for 6, what is the best graph that shows a relationship between frequency and period? Now, if we remember, T equals 1 over F. That's an indirect relationship. And the only one that shows an indirect relationship is that one, which is choice 4. All right, next page, which is number 7. We have a graph that looks something like this. And it wants us to label the proper amplitude and wavelength. Now, amplitude is from rest to crest, so any of these vertically are amplitudes. And the wavelength is one complete oscillation of a particle on the wave. Now, if I look at the diagram, the only one that fits is 3. And that shows the following. It's got the amplitude labeled here, and then the wavelength is just this second complete wave pattern instead of the one I labeled originally, which was the first. So it's got this one and this labeled. So that's choice 3. All right, for number 8. Police cars traveling at a speed of 30 meters per second. So that's the speed of the car. 30 meters per second. And the frequency of the car is 1 times 10 to the 3 hertz. So instead of writing 1,000, they put it into scientific notation to make it look harder. But it's just 1,000. You want to write 1,000? Go ahead. What is a pedestrian going to hear as the siren approaches? Well, this is a Doppler effect question. And we did discuss the Doppler formula, but the choices are as follows. 30 hertz, 9.19 times 10 to the 2, which is 919. 1 times 10 to the 3, which is 1,000 again. And 1.1 times 10 to the 3. Now, all you have to remember is that as objects approach each other, the frequency, the apparent frequency, goes up. So the frequency is going to increase. The only one that's bigger is this one, which is choice 4. So that is a Doppler effect equation. We didn't need the velocity of the car at all. If we wanted to, though, we could actually calculate the frequency that they'd hear using the Doppler equation. But that's not necessarily because there's only one value that's bigger than the original, which is 1,000. This one right here, definitely a trick Watch out for putting 30 hertz and 30 meters per second. The first number there was 30. Sometimes students will just put in the first number that they see if it matches. So watch out for that. We'll reset and we'll do 9 and 10. All right, now on to 9 and 10. Number 9 has two waves. It looks something like this. Oop. They meet at the same point here. And it asks what type of phenomenon is shown when the two waves are occupying the same space at the same time. Now, if you remember, when two waves are both doing the same thing and they try to collide, they form a bigger wave, and we call that constructive interference. So where they overlap, it's going to be constructive interference. And that's going to be choice 2. Now finally, number 10, we have a kid jumping rope. And we have a diagram showing the kids. And this value of 4.3 meters is how far apart the two kids are that are operating the jump rope. And there's a kid without arms. There's the arms. Jumping in between the jump rope. And it asks, what's the wavelength? Now we have to remember that this distance between the kids is actually half a wavelength because it's the distance between two nodes, antinode in the middle. And if we have 4.3 meters is L equals 1/2 lambda, we double it. So wavelength is going to be 8.6 meters. So 8.6 is choice 4. Now you'll notice a lot of these are conceptual. Very little math involved, very little calculations and problem solving. You just have to recognize terms and apply those terms to some unique graph that may be new to you. But since you already know the terms, it's just applying that to the problem at hand. So they should be a little quicker than some of the problems we did earlier in the course. So if you're worried about timing for the state assessments, realize that when you get to the waves section, that's where you'll be able to make up some time if you spend a lot of time on projectiles or Newton's laws or even vectors.